Okay, now next thing is we want to simplify our push-pull amplifier, uh, in the sense that we want to make it more simple. So remember, if you see, this was our original class A B push-pull amplifier. Okay, this is push-pull because we are using two transistors, Q1 and Q2, and this is class AB configuration as well, because we are introducing biasing at the base of Q1 and Q2. So this is basically, I can call over here this push-pull amplifier, but it is class actually class B amplifier, class AB, class AB amplifier, right? Remember, okay, because we have the property of AB amplifier that it rectify, or it removes the crossover distortion, right? So this is done. This is our push-pull amplifier, class AB amplifier. Now since we can see over here there are two equal and opposite power supplies, or one is plus VCC, the other one is minus VCC. So it's better to convert, or to have one power supply actually. So over here this is the modified circuit diagram, okay, and we call this as a single supply push pull. Okay, so we are actually having a single supply instead of a dual supply. Okay, the other one is over here is grounded, so we remove the other power supply, which is minus VCC, or here in this part. So this is the modified version, okay, with a single power supply. So over here if you see the characteristics, that this is a single voltage source, so only VCC is present. The circuit operation is same as described previously. So basically the operation mechanism, okay, is the same of this circuit is actually the same as this one. Okay, but there is, except the bias is set to force the output emitter voltage to be VCC divided by 2 instead of 0 volts, right? Okay, so basically I can make this speaker off so that you can, there is no disturbance. Okay, okay. Now what happens, that what does this actually mean? Okay, so what does this basically, this voltages mean? So if you see the voltage at this emitter is your this point over here. Okay, this is your emitter terminal. So basically if you see, first we explain the previous circuit over here. Now last time uh, we analyzed the circuit, and we said that this circuit, this part of the circuit, is exactly the complementary of this part. By complementation we means that they are uh, mirror to each other, in the same end mirror. It means that their operation is dual operation, and they actually what happens over here on the next half cycle, it happens in this part, right? Okay, so we proved that at this point, okay, because of the value of VCC R1 and D1, which is the same as minus VCC R2 and D2, this forces the voltage at this point, which is point A, is equal to 0, right? Okay, so it means that this VA is equal to 0. Okay, now the property of this circuit is that it would transform this voltage at this point, which is your emitter point. So basically if I draw something like this, that if this is an emitter, right? Okay, okay, so basically this is your RL resistor. Okay, this is a resistor connected. Okay, and this is your the L is grounded. I'm talking about this part, right? Okay, so over here, from here to here, okay, this is VE. Okay, and you can prove that. Okay, now remember this thing, and if you see, this is the diode part. Okay, and this is the point A part, actually this one. Okay, so the property is, if this is equal to at 0 volts, okay, this is, remember, transistor, this is its, okay, collector part, this one is connected to its collector, okay, and this is D1, okay, this is D1, this is diode D1, okay, and here you have the resistor R1. So basically this, if this is equal to this A point has a value of 0 volts, so by KVL we can also prove this, it is that this is equal to VE will be equal to 0. You can prove using using what, using KVL over here in this loop, over here in this loop, somewhere in this loop, right? Okay, so this VE is equal to 0. So if this is the case, okay, so it means that VA is 0, okay, so VE is basically voltage at the emitter is also equal to 0. Okay, now what should be VC then? VCE then, VCE, remember that VCE would be equal to your VC, okay, which is equal to basically VC and minus VE. Okay, so what is VE? VE is 0, you can put the value VE is 0. Okay, so and what is VC? VC is over here, which is VCC. VCC. So it means that VCE comes out to be VCC. This thing comes out to be very simple. This is VCC. So it means that what is VCE now? VCE would be the drop over here between this point and this point. Okay, this is your collector point and this is your emitter point. So that's why, okay, if that's why we call over here the VCE over here, okay, between these 2 points, okay, VCE is equal to VCC. Okay, this is VCC. Now if I, okay, now coming to the modified form, this is the modified version of this by modified version means that only single supply over here. Now by a single supply, now this was, remember the point, let's suppose this was the point A. Okay, now we cannot say that actually over here the voltage is 0. Why? Because this is VCC and this is at 0 point, at 0 volts. Okay, so it would not cancel the effect of both the circuits. Okay, they would not push each other to have this circuit, and this circuit would not push each other to have resultant voltage equal to 0, as in this case. Okay, why? Because this is VCC and this is not equal to this over here. This was VCC, so let's suppose it was like 9 volts, let's suppose. So basically it will be minus 9C, minus VCC means minus 9 volts. So this arrangement makes VA equal to 0, but over here I cannot say this will be equal to 0. So if this is not equal to 0, so it means that, okay, the biased, okay, the output is not biased as 0 volts, number one, we will consider this. Okay, but we say we have to now introduce, okay, insert a capacitor C1 and C2 to block DC, okay, going towards the source over here. Okay, over here there was no capacitor, we did not need any capacitor. Why? This was equal to 0, so biasing at this position was 0. Over here we need the biasing is not non-zero, so actually we need these two coupling capacitor okay, to make sure the netting goes, the DC doesn't affect your input source. Okay, now so when this A point is not at 0, so the question is what should be the value of this A point. So over here by default, for this arrangement, for a single supply, we can, okay, we say that VA over here is equal to, it should be VCC divided by 2, actually VCC divided by 2. Okay, so if A is equal to 0, so by definition, by this characteristics, VE, it implies that actually VE would be also equal to VCC divided by 2. VCC divided by 2. So where is VCC divided, where is VE? VE is over here. Okay, this is VE. So it means that, okay, now, so if this is VCC divided by 2, this point, okay, so what should be this point? This point. So this is your VCE, your VCE. Okay, VCE. Okay, let me can't find any mouse over here. Okay, so VCE is equal to, it is equal to VC and minus VE. Okay, okay, now what is the value of VC? This is, okay, VC is over here, so this is VCC. Okay, and this is, what is the value of VE? Now this is equal to VCC divided by 2, VCC divided by 2. Okay, so it means that the value comes out to be this one, VCC divided by 2. Okay, this is the value. If you go, this is 1, this is half, it will make it half. Thank you.